All right, let's get right into it. We hear all the time about the amazing things AI can do, but have you ever stopped to think about how it really learns? I mean, what's actually going on under the hood? It's not some kind of black magic, it's actually a pretty structured process. And today, we're going to pull back the curtain and look at the hidden rules that make it all possible. And it's totally understandable why it feels like magic, right? You feed a bunch of data into this machine and suddenly it can pick your face out of a crowd, translate languages on the fly, or even write a poem. It's just this incredible feat of engineering that honestly, a lot of the time feels completely unbelievable. So, that's the real question, isn't it? How in the world does it pull this off? What is happening behind the scenes that takes a model from basically knowing nothing to making these super intelligent predictions? What's the blueprint for learning? Well, the secret, it turns out, comes down to two really fundamental concepts. Now, they've got some technical sounding names, but just think of them as the two silent architects that design the entire system. They shape everything an AI model can do, and just as importantly, what it can't do. And they do all this before it ever sees a single byte of data. Okay, first up, let's explore the model's playground. You can think of it as its realm of possibility. In the biz, we call this the hypothesis space. But hold on, before we dive into the space part, what even is a hypothesis in this context? Well, in machine learning, it's really just one possible explanation for the data you're looking at. Think of it as a single, simple rule, like if an email contains this word, then it's probably spam. It's just one guess, one theory about how things work. Okay, so if one hypothesis is one guess, then the hypothesis space is the entire library of every single possible guess the algorithm is allowed to consider. And this is key. It's not infinite. It's a predefined set, a menu, of all the potential answers the model can even think about choosing from. I've got a great way to think about this. Imagine I give you a pencil and a ruler, and I say, draw a perfect circle. The catch? You can only use straight lines. What happens? Well, you can draw a triangle, a square, a pentagon. You can even draw a polygon with 1,000 sides that looks almost like a circle. But no matter how hard you try, you will never, ever get a perfect smooth circle. Why? Because your tool, the straight line, limits your possible outcomes. And that is exactly what a hypothesis space does for an AI. The right answer, the perfect circle, has to exist within its predefined space. If it doesn't, the AI is never going to find it. Period. And here's the thing. This space doesn't just appear out of nowhere. It's not random. It's deliberately designed by the person building the model, by you. The second you decide to use, say, a simple linear regression model or a big, complex neural network with a certain number of layers, bam, you've just defined the boundaries of that playground. You've set the rules of the game. This idea connects directly to something we call a model's capacity, which is just a fancy way of saying how well it can learn complicated stuff. So a simple linear model, it has a pretty small hypothesis space, so we say it has low capacity. It can only draw straight lines, basically. But a deep neural network, whoa, that thing has a massive hypothesis space, giving it super high capacity to learn all sorts of incredibly intricate patterns. All right, so the model has its menu of possible answers, its hypothesis space. But wait a minute. Having a huge space can actually be a problem, right? How does the model navigate this massive library of possibilities? It needs a guide, a helping hand. And that brings us to our second silent architect, inductive bias. So, just to recap where we are, the hypothesis space lays out the menu. It tells the model, here are all the potential solutions you're allowed to even think about. But here's the puzzle. Even with that menu, especially if it's a huge one, there can still be a ton of ways, sometimes an infinite number of ways, to explain the same set of data. So how on earth does the model pick the best one? What's stopping it from choosing some ridiculously complicated, convoluted answer when a much simpler one would work just fine? And that is where inductive bias saves the day.
It's basically the model's built-in set of assumptions. It's a preference, a nudge, for certain kinds of answers over others. It's the little voice in the algorithm's head that helps it choose one hypothesis and, this part is absolutely crucial, helps it generalize to new data it's never seen before.
Okay, here's the perfect way to picture this. Imagine I give you a piece of paper with 10 dots scattered on it, and I tell you to connect them. Now, you could draw a crazy, wild, jagged line that zigzags all over the place but hits every single dot perfectly. Or you could draw a simple, smooth curve that flows nicely through them. What does your brain want to do? Probably draw the simple curve. Well, inductive bias is what tells the model to do the same thing, to prefer the simplest, smoothest curve. Why? Because that simple answer is way more likely to be the real pattern, not just random noise. It's basically Occam's razor for machines.
And this bias, it kind of comes in two main flavors. First, you have what's called restriction bias. Think of this as a hard and fast rule. It actually shrinks the hypothesis space. So when you decide to use a linear model, that's a restriction bias. You've just told the model, hey, nonlinear answers, not even an option, forget them. Then you have preference bias, which is a bit softer. It doesn't throw any answers out, it just ranks them. It says, look, all these answers are possible, but I'm going to give bonus points to the simpler ones.
So there we have it, our two architects. One draws the map, setting the boundaries. The other acts as the tour guide, providing directions. Now let's put it all together and see how this two-part blueprint really works in practice. All right, let's boil it down. It's this simple. The hypothesis space defines what is possible. That's it. It draws the map, laying out every single road the model is allowed to travel. It's the entire universe of potential explanations. And then the inductive bias defines what is preferred. It's the GPS for that map. Out of all those possible roads, it tells the model, hey, take this one. This route is probably better, it's simpler, it's more likely to get you where you need to go. It's the assumption that lets it make a choice. Okay, so why are we geeking out about this? Because understanding this blueprint isn't just some abstract theoretical exercise. The choices we make about these two things have massive real-world consequences for how AI models actually work. So let's talk about why this really truly matters. It all comes down to a balancing act. If you get it wrong, you run into the two most classic problems in all of machine learning. If your hypothesis space is too small, remember trying to draw a circle with only straight lines, your model just can't learn the real pattern. We call that underfitting. But on the other hand, if your space is huge and your inductive bias is too weak, the model gets obsessed with the training data. It learns every little quirk and bit of noise, and then it completely fails when it sees new data. And that, my friends, is overfitting. This whole idea leads to a really famous concept in machine learning called the no free lunch theorem. And what it basically says is this: there's no magic bullet. There is no single learning algorithm that is the best for every single problem out there. Why? Because every algorithm has its own inductive bias, its own set of built-in assumptions. So the best algorithm always depends on the specific problem you're trying to solve. And this right here is where it all becomes so powerful for you. Because every single decision you make when you're building a model is actually you manipulating these concepts. When you choose a particular model, you're choosing a hypothesis space. When you add something called regularization, you're applying a preference bias. When you engineer your features, you're injecting your own assumptions. You are the architect, you're in control. So what's the big takeaway here? What's the one thing to remember? It's that machine learning is never assumption-free. In fact, it's completely driven by assumptions. So when you choose a model, you're doing something pretty profound. You're embedding a belief system into your AI. You're telling it how you think the world works, that you believe the relationship in your data is linear, or that simpler answers are always better. You're not just picking an algorithm. You're choosing a philosophy. And that single choice, well, it determines everything that happens next.